as well as working on this federal contract and supporting the science and engineering that goes in behind this. So we've got an interest in the development of this model and its applications. We've got stakeholders that we are able to test these tools out. For me in Colorado, we do a lot of drought work. You're probably aware that Colorado is a headwater state and the entire Western US is in a chronic drought right now. So that's having profound implications, really exacerbating where we are with economic concerns right now, and recessions and so on. So reductions in yield, reductions in hydropower generation, and increasing numbers of wildfire. And I was really disappointed to miss some of the earlier sessions this week. I'm sorry I'm late, but there was a good compound flood and hazard session that I would like to have taken part in. But a lot of the floods that we react to are primarily a function of rainfall runoff events on wildfire burns and all the implications there with that manifesting often as debris flows. Oh, it's not now going forward. So I've worked a lot on the ground with floods like the 2013 flood front range event. So I got up to Jamestown, a small mountain town on the receiving limb, and realized that they suffered flood damage for sure, but it was really a high concentrated debris flow torrent that came through their town, killed some people and caused immense amounts of damage. So I've been helping the state in Washington and in Colorado develop channel migration zone guidelines to recognize that in many places, at least in the Western US, channel migration is more of a hazard than overbank flow in terms of the channel will frequently change direction. So just wanted to give you that preamble to sort of highlight what the Weather Service is trying to do here. This is really a paradigm change. For nearly 4 decades, the National Weather Service river forecast centers in the major basins, and by major, I'm talking about the Mississippi, the Columbia, some of the big rivers that I'm sure you're familiar with. They've really delivered just thousands of key forecasts along those main stem river locations. And that's got limitations in terms of how useful that is to stakeholders on the ground, because you then have to take that data and extrapolate out. So the goal of the National Water Model was really to densify that network of forecast points and take it from the thousands to several millions using a geospatial hydrofabric, essentially the national hydrography data set, NHD, which was developed by the USGS a few years ago to facilitate that. So that's the work that we've been doing. The goal of the Weather Service in developing more forecast points is really to take flood forecasting to the masses, to make it more useful to more folks at different scales, not just regional, but drill down to state and local concerns and enable them at least to have some information to be able to extend the forecast to their place of interest. So we'll look at some of the key components that my team have been working on: the hydrofabric development, the next generation hydrology that we're developing as the sort of engine room of this model, the inland routing and coastal coupling. That's been a key feature of this model, is that we're coupling terrestrial fluvial hazard models with coastal hazard models. I'll talk a little bit to that. And then at the business end, the decision support end, what are we doing with flood inundation mapping and turning that into actionable intelligence? So the hydrofabric, well, what is this? A lot of you will be familiar with all the geospatial work that we all have to do to set up our models. And that essentially focuses on getting the blue lines. That's the NHD data set that I'm referring to, that a lot of this work is based on. Flow path and flow line catchment geometries are efficiently and effectively set up, and then making sure they connect and transfer water and energy through those flow lines and into the catchment that's downstream. We then use that information to attribute, essentially to parameterize whatever model that we're using, but then also to develop new attributes that can be used by decision makers later on in the modeling process. And then all of the software and data models that we need to be able to create that and keep a consistent data infrastructure. So that really just summarizes what I just said. You've got the blue lines, which is the key computational fabric, the topologies linked together, all of those aspects. The attributes provide the information for the model execution for very data hungry models, and models that quite often need different sorts of information from this hydrofabric. And then a community focus that really enables other folks to be able to contribute to and test all of this hydrofabric information, but apply it to a lot of different models, not just the National Water Model. So the process that we've been using here has been highly collaborative. So we're working with other agencies, including the USGS. The NHD has been wonderful for a number of different applications, but we soon realized that it wasn't perfect for this task. And in fact, there's idiosyncrasies and I guess problems with the data set from the point of view of doing flood routing and forecasting, and that sometimes things don't connect the way they should do. Blue lines don't sit. Somebody brought up the issue of the temporal utility of some of these data sets based on the DEM that they've been extracted from. So there's a lot of reason why we need to sort of get a systematically developed hydro fabric that supports a number of different types of models and modeling operations and agencies. So all of this is getting called what we call the reference fabric. So it's got a number of data model interfaces and other tools that we can use to be able to ingest that into the public domain and make that freely available. So the real strength of this data is not just that it's going to be supporting the national water model, but that it's going to be freely available to many other folks, maybe to couple up with freely available DEMs. And obviously the topologic boundary condition that Lawrence was talking to is a big part of this. Its real utility is that we want this to be available for all different types of models, not just one model, so that the appropriate model can get used based on the processes and the location of concern. And I'll talk to the importance of that in just a moment when we look at the next gen task. And then one last thing on the hydro fabric is really optimizing it so that we're looking at the appropriate density of stream lengths and reaches, and also the sizes of the watersheds or sub-watersheds that we're looking at. So for finer scale modeling, obviously you want to drill in and look at a higher resolution hydro fabric. For more synoptic or regional modeling, you'd want to be able to scale out, and testing that to see at what scale we need to bring in the hydro fabric for what type of model or region is really important. So the hydro fabric really sits in the lower left-hand corner of this entire project, but it is critical, as I'll re-emphasize in just a moment. So the next generation hydrologic modeling, this is really just moving on from, we've been using one model up until now, Wharf Hydro. The realization has steadily evolved that having a suite of models and being model independent is critical so that we can account for the physiographic and climatologic variability of the United States, which is obviously quite profound given the scale of the continent, and being able to apply the appropriate model at the right time for flood forecasting. So for example, in Cascades and or Sierras, you might be more interested in a model that's got physically based and distributed information on snowpack and be able to emphasize that. So that's a really important part of this project, and recognizing that no hydrologic literature tells us this, that no one model is really going to represent processes everywhere to the resolution that we might need it, particularly for forecasting. So it's really an abstraction of reality, and we need to be able to slot in the model that we think is the best fit for that forecasting location. So again, we're looking to move towards a modular framework. That's the key advance that we're making with the next generation system. So just to highlight what one of the advantages of that modular approach might be, this is a traditional workflow for a hydrologic model setup. So we're going to develop our parameters, forcings, and geospatial input data of the hydro fabric for, in this case, Model X. And then from Model X, we will then run that after we spent some time and energy setting up and get output data. And then we might look at the results from that and realize, well, it's really not very good. You see there that we're not getting a good representation of either the time of the flow or the peak volume. So we might then do some work, and this is where we really get into the hydrologic science part of this in terms of calibration, and then trying to improve the performance of that model. So in this case, the calibration has improved at least the volume, but not the timing. So that's important. Obviously, if we're some hours, and in this case, it looks like quite a considerable time out, then it's not going to be very helpful for forecasting if we're getting the peak way too early or way too late. So what might we typically do then? Well, in many cases, we start to think about using a new model, and that's extremely time-consuming and expensive, and that we have to go through that whole process again. So this is what we're really trying to move away from with the next generation hydrologic modeling framework. And it's just indicating the recalibration. By creating the modular framework, once we've got our consistent hydro fabric set up, once we've got our consistent forcings and an understanding of how they need to be formatted, And we have the ability to plug and play a number of different models in a very model independent, and by the way, code independent way, using what we call BMI, which is a modeling interface that we're using for this process. Then you don't only have to rely on the models that we, the Weather Service and their contractors are providing you. You can also bring in your model. And then once you're set with that, you can then start to calibrate in a much more efficient way, because you're not having to reset all of the initial input data, which is often the most costly part of the modeling process. And then we can do interesting and useful things like compare models and see which one is the best for the physiographic and or the climatologic circumstances in which we're trying to forecast. You only need to change some of the core configurations. All of the input parameters, the geospatial fabric stays the same, and even the run commands stay the same with the BMI approach. There's a lot of efficiency there, and that enables us as hydraulic modelers to focus in on what we really want to spend time on, which is fine-tuning of the calibration and or testing different models and or applying them in new and creative ways, and looking at, for example, the hydrologic impacts of climate change, for looking at water supply under climate change projections and other applications, not just spring flow forecasting. So we, Linker, are collaborating obviously with our client, the NOAA National Weather Service Office of Water Prediction, based in the National Water Center in Tuscaloosa, Alabama. And I've got quite a few colleagues here today, Sagi and Jim and a few others that have worked on site or continue to work on site down there. And some of that's now in collaboration with a research group, the Cooperative Institute for Research Operations and Hydrology. I think I've got that right, Sagi, Cairo. So this is based on the University of Alabama site. And this is also funded by NOAA, but is essentially bringing much more of a community together to support the federal government do better science to augment the development of the model and improve the quality of the forecast output. So the inland routing, obviously critical in terms of getting all of this hydrologic modeling represented once it gets into the channel and get the timing of that right. Up until now, we've been using very simple one-dimensional flow routing algorithms, and that's partly computationally limited. We're also starting now to look at using more sophisticated routing techniques, particularly at the coast, where we've got compound channel issues in estuarine environments, and or we're starting to look at the coastal coupling challenge that I mentioned earlier. So this is a critical part of the process, but also a challenging one, especially now when we're starting to look at regulated systems and starting to contemplate what we're going to be doing with reservoir releases on regulated systems. I'm going to skip the coastal coupling really quickly and just give you a heads up on what that's about. So, you know, this really is a big breakthrough. This is really being driven by the Coastal Act, and this is NOAA's commitment to FEMA to be able to help them differentiate between whether coastal properties are getting damaged at the coast by tidal, really flood action and or wind action, and being able to separate those two out from the point of view of paying out federal insurance claims. But that's really motivated, you know, an understanding that really, especially with some of the big tropical storms that we get in the US. So I'm thinking here of things like Katrina, Harvey, Sandy, that drive a lot of water onshore at the same time as those same storm events are dumping a whole bunch of water inland that's then trying to get out, is really to get the peak of the discharge and the flood inundation at the coast, which is where most of our population lives, as best as it can be. We really need to tightly couple appropriate coastal models with the inland hydraulic models. So that's a big part of what we're doing under this development, and we'll continue for no doubt the next several years to refine that. So stream flow forecasts in themselves have great value for a number of consumers, Corps of Engineers, some emergency management capabilities, and obviously the river forecast centers is a key client of the National Water Model. But really, a lot of folks want to understand more about what the implications are of that at the damage end and impacts on infrastructure. So real-time flood forecast inundation mapping is a big push for this project in terms of being able to put out real-time inundation maps, or to facilitate communities and cities do that work themselves without having to set up their own forecast model, which is obviously very expensive and cost prohibitive for most cities, frankly, to be able to develop and maintain an operational forecasting system that's got this capability. So getting partway there is really important. The Weather Service is investing in tools and techniques which can help folks get partway there. So we're using a technique called HAND, which is the most computationally efficient, probably the least technically sophisticated, but does represent inundation fairly well in a number of locations, but also falls over in a number of others. So we're working right now to validate where and how in different types of physiographic conditions, different geomorphologies, tubular geomorphologies, it's working and where it isn't, and what we need to do to help fix that. A really important project that Jim supported, Jim Nelson, is the National Flood Interoperability Experiment, which is a summer internship where for 6 weeks students come into the National Water Center and work on a whole bunch of different application areas in and around this project, but FIM has been one of the key ones, and testing and refining HAND has been one. Testing other models to see if they've got more suitability. So, we heard from Lawrence earlier. He's working with Fathom and the group that Paul Bates is a big part of, so using ListFlood, which is a big part, as I understand it, of some of the work that they're doing in their flood modeling and seeing what potential that's got. And then utilizing all of the inundation maps that the Corps of Engineers have developed over the years, because that's a great tool for us to use for validation, calibration, but then also potentially for developing various types of index maps that we can bring up, which is a very computationally efficient way to reference stage discharge relationships to an index map and bring that up instead of trying to draw the map on the fly in real time. And then just lastly, the communities that really matter here, we're looking at how to translate this information, whether it's some of the bigger synoptic information at the global, the CONA scale, or the regional scale, right down to local municipalities, and trying to understand, is it real-time inundation maps they want, or do they want to understand what the impact's going to be on different types of infrastructure, lifelines for evacuation and optimizing that, or do they want to know what residential, commercial and industrial infrastructure damage is likely to be in 10 minutes or a couple of hours or days or after the event for insurance purposes. So we've created a whole suite of tools where you can see forecasted out based on the National Water Model forecast which buildings are going to be damaged and how badly, which lifelines are going to be dissected and may actually prevent folks from getting out of harm's way. So this is a big step forward for the US in terms of trying to do this as a global project across the entire US. And as I mentioned, it's in collaboration with a number of different agencies and increasingly with the global hydrologic community. Thank you.
Thanks for the presentation. Questions, I'm sure there's one. Can you itemize 3 main priorities for next year in terms of modeling, in terms of
sure. Yeah, and I've got to reflect here. I am not speaking directly on behalf of the Office of Water Prediction. This is just my perspective as one of their key supporting contractors. So I would say the modularization component is key, and making that real and truly accessible so that folks are not only able to plug in their own model, they're actually able to get the code and take that next generation hydraulic modeling system out and scale it. Secondly, what's a big part, and that's why I emphasize the development of Hydro Fabric. I spent 10 years of my career, 3 years, as a grad student, when it was quite exciting to work in the geospatial domain, especially for folks, in a Germanized age bracket where geospatial science and technology was brand new and it was an exciting thing to do. Now, of course, it's just a big time sink, but a lot of these tools are available, but they are not necessarily, one size fits all. So trying to get the Hydro Fabric so that modularization can be effective is key. And then thirdly, I would say the collaboration with the project that Sagi and others are going to be working on, and with the Cooperative Institute. So I feel that federal government at least gets constrained, and they have to do what they've got to do, and they've got to do it in a timely fashion, and they've only got so much money to work with. And I think what the funding that the Cairo group has gotten then is going to facilitate all of the operators working within that research group to extend out to the bigger community effectively. So assimilating all of that great knowledge that's out there from all of the other folks around the world, Deltaras and all the other groups, GeoGlows, that have done this sort of work to get their information brought into the federally funded operational domain. That's just my thought, just to be clear. Sorry.
Thank you for the presentation. So we heard quite a bit this week, and generally we hear a lot about machine learning use in this kind of research and development. Do you have any thoughts on the use of it?
Yeah, so the question, if you didn't get at the back, is on, you know, where machine learning is going in this domain. I would say on one hand, it's pretty terrifying because some of the folks that are turning up some of the machine learning, you know, model offs, the model comparison experiments are doing exceptionally well against models that have taken years to set up and parameterize and fine tune. So it really does make you scratch your head and ask, how could that be? But they're also very black box, so it's not necessarily clear how they're able to do that, other than some skillful programming and the vast amounts of big data that are out there that do make cool things happen when you've got great coders and some good scientists behind it. So I guess my response to you is I think it's going to be something that complements hydraulic modeling into the future. And you know, I guess as a hydraulic scientist and others really want it to take over and let's just hand it off to Google or somebody to do all our modeling for us. But it's definitely a tool, right? It's something that we can use to help at least characterize and possibly improve our modeling. And it is really exciting. I mean, terrifying and exciting. Right?
Okay, I think we have to move on. So